In this video, we are going to explain Superlens, which is a type of metamaterials and is used to form high-resolution images. In image formation by normal lens, as the light waves at different distance from or incident on the lens at different angles, they all bend by different angles and converge at a point theta, and hence the image formation takes place. Each object has its own diffraction pattern. Our eyes can differentiate between two objects if the distance between the peaks of diffraction patterns of two objects is greater than diffraction limit. Resolution of image depends on the wavelength of light used, as the wavelength of diffraction pattern depends on the wavelength.
Evanescent wave. The fine details of an object is encoded within the evanescent waves. They decay exponentially in the direction of propagation, and it results in the loss of information of these details. This is the reason why we have a diffraction limit on the resolution of an image formed by a normal lens.
So, how to get the information stored in evanescent waves? To get the information stored in evanescent wave, we need to somehow get the evanescent waves to propagate without decaying. In positive refractive index materials, the evanescent waves decay exponentially. And so it was proposed that a material with negative refractive index would be able to capture the evanescent waves. What is the effect of negative index of refraction? According to Snell's law, n1 sin theta 1 equal to n2 sin theta 2. If n2 is negative, then the angle of refraction must also be negative.
Imagine what would happen if water had negative index of refraction. The glass on the right shows a hypothetical water with negative refractive index.
Can we have a material with negative refractive index? For a material to have negative refractive index, the permittivity and permeability of the material should be negative. Unfortunately, no such material exists in the nature. But by artificially engineering metamaterials made of metal loops and wires, we can tune the values of permittivity and permeability to those that are not accessible by nature. Effect of negative index of refraction on propagating and evanescent waves. For propagating waves, because of the negative index of refraction, all the divergent light waves converge, and as the total phase change is zero, it leads to the formation of an image. Evanescent waves. Inside the lens, the evanescent waves are enhanced, and outside the lens the waves decay, which result in the same amplitude of the original level at the image plane. Thus, by recovering both propagating and evanescent part, a better image compared to normal lenses is produced.